Good morning, everyone. My talk today is going to be about mapping poverty with satellite imagery and machine learning. Like Derek said, I'm a third-year PhD student at Stanford, and I do research in machine learning and work with Stefan Rahman. This project has also been a collaboration with researchers in the Earth System Science Department here at Stanford. So reducing and eventually eliminating poverty has been a goal of humanity for a long time. In fact, the elimination of poverty is the first of 17 SDGs set by the United Nations for the year 2030. The current international poverty line is $1.90 per person per day, and it's estimated that around 700 million people still live below that standard. So the UN SDGs provide a great target for the world to shoot for, but it doesn't really matter how many goals we set if we're not able to measure our progress towards those goals and figure out how to improve. So traditionally, we've used nationally representative household surveys to collect data and monitor poverty and wealth. However, for many countries, especially the poorest ones, they don't have the resources to send people out into the field and conduct surveys that have good temporal and spatial coverage. In Africa, many countries didn't conduct a single survey during the previous decade. Even when surveys are done, they typically reach less than 1% of all households, and leave many of the poorest people in the world effectively invisible. So this plot kind of shows on the left the number of surveys in each country that captured consumption or income, and on the right the number of surveys that measure asset-based wealth. Without reliable data, it's hard for policymakers and aid organizations to enact effective policies and distribute their funding effectively. So there's a huge need for new and creative solutions that can fill in these data gaps. Part of the inspiration for our project came from a paper that was published at KDD in 2014 by an NGO called Give Directly. So Give Directly does direct cash transfers to the very poor. And to do this, they need to be able to locate extremely poor villages and then target individual households. Their insight was that satellite imagery could be used to find the poorest villages. Using traditional computer vision techniques, they detected roofs in satellite images and classified them as having either metal or thatched roofs. Villages with higher proportions of metal roofs were ranked to be wealthier, and this automated ranking system helped them cut costs and deliver cash efficiently, because then they could just send people on the ground out to only the villages that they predicted to be poor. So satellite imagery is constantly getting better and better. There's companies like Planet Labs today that are sending up satellites that can, they hope to monitor the world every day. And high-resolution satellite images contain a wealth of information beyond just thatched and metal roofs. So as humans, we can look at these two images and extract a ton of useful information. For example, to me, the one on the left looks like a busy shipping yard, while the one on the right is more of a suburban or rural area. And your own interpretation might be a little bit different, but the point is that by using what we know about the world, we can tell rich stories just from these static images. But to a computer, these images are all unstructured data. So how do we make sense of trillions of raw pixel values? This is where deep learning comes in. In the last few years, convolutional neural networks have achieved unprecedented success on a wide variety of computer vision tasks. Deep neural networks are composed of layers of neurons. So lower layers look for simple image features like edges and corners, while higher layers put those low-level features together into more complex shapes and objects. Compared to traditional computer vision techniques that require domain knowledge and lots of manual feature engineering, deep learning models automatically learn good feature representations. One common machine vision problem is image classification. In the example here, we want to label images with the type of animal that is shown. So we can train the network by feeding in images and making predictions. Sometimes the network will make a mistake. So in this example, it predicts raccoon for this image that actually shows a honey badger. And when this happens, the network gets feedback through a process called backpropagation, where the mistake is propagated back through the neural network, and all of the parameters in the network are updated to make it less likely that the same mistake will be made again. So this is what we mean when we say that we are training the neural network, or that is learning. So images are very high dimensional and can obviously be extremely varied. In order to train a deep neural network that has millions of parameters, we need to feed the computer thousands and thousands of labeled training examples. For poverty, this type of direct supervision is impossible because we have very little ground truth data. Ideally, we'd like to show the computer lots of satellite images that are labeled as either rich or poor, but we just don't have that much data on poverty. And that's basically why we wanted to predict poverty in the first place, is to be able to fill in these data gaps. So transfer learning is a technique in machine learning that can help us to overcome this data gap. The general idea is that if you have a target task that is difficult, in this case, the poverty prediction task is hard because there's not very much data to train on. You can start by learning how to do an easier task and then transfer what you learned to help you solve the harder task. My favorite analogy for this comes from the movie Cool Runnings. So if you guys are familiar with this movie, there's a Jamaican bobsled team that wants to compete in the Winter Olympics. But this is a very difficult task because Jamaica is very hot and there's no ice anywhere. So since there is no ice in Jamaica, they instead train on a dirt hill in a bathtub on wheels. And in the end, they apply the transferable skills that they picked up to compete in the Winter Olympics. So Cool Runnings came out in 1993, and in 2014, machine learning researchers finally discovered that transfer learning works quite well for computer vision problems as well. So back to our problem. We don't have enough poverty data to train our deep learning models directly, but we can take a transfer learning approach. Instead of trying to predict poverty right away, we're instead going to start by training a model on the easier task of predicting nighttime light intensities from daytime satellite imagery. This is a task where we have plenty of training data because we collect nighttime lights by just taking a satellite image at night, and nighttime lights have been shown to be correlated with economic development. This is kind of a famous picture of North Korea and South Korea at night, and South Korea basically looks like an island because North Korea is so dark. One obvious question that you might have at this point is, why don't we just use nightlights directly to predict poverty? And you can do that, but nightlights have a couple major weaknesses. For one, nightlights show very little variation in the poorer parts of Africa. So in very poor places, nightlights are almost uniformly zero. So if there's no variation in this measure, then we can't really hope to predict variation in the output that we care about. Second weakness is that nightlights are easily fooled by population density. So a nightlight's value is just a single scalar value, and it can't very easily distinguish between a sparsely populated rich area and a densely populated poor area. To nightlights, these two places could look very similar. So we would like to also use the information in daytime satellite images to inform our predictions about poverty. So here's what we're going to do. We're going to start with the easier proxy task of predicting nighttime light intensities from daytime satellite imagery and train our neural network on that task. So through this training, our convolutional neural network learns to represent each daytime satellite image as a lower dimensional set of image features that is useful for predicting if that location has low, medium, or high nightlight intensity. After training the CNN on the nightlight task, we fix the parameters of the CNN, and then we use it as a fixed feature extractor. The CNN allows us to map each satellite image into a feature vector that summarizes the information in the image. These features can then be used as input to a second model that predicts poverty. So Our model has learned to find features in the daytime satellite images that are useful for predicting nighttime light intensities. The big question now, and the hope is, that some of these features are also going to be useful for predicting poverty. So as some of you might know, deep neural networks are not always the most interpretable models, but there are some things that you can do to kind of visualize the types of features that you are learning. So here on this slide, highlighted in pink, are 4 examples of the features that our model learns to find. So each of these columns represents a different filter in our network, and the first row is kind of raw input satellite image. The second row shows the activations for each of these 4 filters on the 4 images in the top row. And then the third row is kind of these filter activations overlaid with the original images. So a filter activates most strongly when it kind of finds something that it's been trained to look for in the image. So you can see that roughly these 4 filters are looking for urban areas, non-urban areas, water, and roads. So these are just 4 filters out of the many that are in the neural network, and not all of them are as interpretable as these, but this gives us some hope that we are finding things that are semantically meaningful to humans. So the next step is to use these satellite image features and the ground truth that we do have, which comes from household survey data. And we use those survey data as the labels, so we can train a second simpler model that can predict poverty. So for this step, we use a ridge regression model, which is a linear model with L2 regularization. And since this model has much fewer parameters than the neural network, we can hope to train it using the limited survey data that we have. So we actually use data from the LSMS and DHS surveys, which many of you are probably familiar with, and we're able to build models that use the satellite image features to predict consumption expenditures and asset-based measures of wealth. Our models can make predictions for any location where we have satellite imagery, allowing us to create fine-grained maps of poverty. This is a huge advantage over traditional surveys, which are usually prohibitively expensive. And in some conflict regions, it can even be dangerous to try to go out on the ground and conduct these surveys. For example, I was talking to someone from the World Bank, and they told me that in parts of Africa, they've had to switch completely to phone surveys because too many of their staff members were being kidnapped. So if we can make these predictions from satellite imagery, we can do this kind of safely from our offices and homes. So here are some poverty maps that we've produced for Uganda and Tanzania where we've aggregated our predictions to the district level. I apologize for the color if anyone is colorblind, so kind of colorblind friendly versions of these are available online. So Uganda and Tanzania are pretty similar countries, both in geography and in socioeconomic profile. But these 2 countries, Malawi and Nigeria, are quite different, and our model is able to pick up on that. Malawi on the left is one of the poorest countries in the world as measured by most measures, but by per capita GDP, whereas Nigeria is much better off, especially in the south, which is more developed and has richer natural resources. Our hope is that maps like these can help to guide decision making for the people who are out there working to make a difference in these places. Another question that we wanted to answer was whether a model trained in one country could predict poverty well in another country. And the reason that we wanted to answer this question is if you think back to that early slide that showed how many surveys had been taken in every African country over the last decade, there are a lot of countries where there's no survey data available at all. So without any survey data, you can't really train a model specific to that country. What you can do is train a model in countries where survey data is available and then try to apply that same model to the country that has no survey data. So this figure is kind of hard to read, but basically on the x-axis, it shows the country where the model was trained. And on the y-axis, it shows the country where the model was evaluated. So it turns out that models generalize pretty well, meaning that we can probably generate reliable poverty estimates even in countries where there's no survey data. And we found that a model trained on data pooled from all of the countries, pooled together from all of the countries, performed best on these out-of-country tests. And you kind of see some things that you would expect here, which is that countries that are relatively close together and relatively similar, their models transfer pretty well back and forth, and countries that are more different, their models don't perform as well when you try to apply them in other countries. So for a long time, Africa has been kind of shrouded in darkness. In a literal sense, the continent is dark at night since access to electricity is limited. But more importantly, the continent has lagged behind the rest of the world in most measures of development, such as poverty, wealth, hunger, and education. So we need new and better sources of data to help turn this tide. And our models still have a lot of room for improvement, but I think we've kind of shown the potential for machine learning to provide better data on poverty and potentially other outputs that we care about around the world. As a grad student, I'm not enacting policy or deciding where aid funding should go or working in the field to help people find their way out of poverty. But I hope that the people who are, including some of you here today, will continue to be open to creative new ideas for making the world a better place. So hopefully you're interested in learning more. Please check out our recently published paper in Science or visit our group's website. And thank you for showing up today, and I'm happy to try to answer any questions now.
This question is from Pawan Gupta, and the question is what do you mean by daytime images, raw RGB or spectral radiance reflectance, is the question.
Yeah, that's a good question. Up to this point, we've been using just RGB images, but we're currently looking into using multispectral daytime images.
Great, thank you. The next question, Neal, is also from Pawan. How do you validate the model performance?
Okay. Yeah, so on the nighttime lights task, it's basically, I'm not sure which task you're asking about, but on the nighttime lights task, it's a 3-class classification problem. So we can just kind of evaluate the accuracy on this by splitting into like a training set and a test set. When we're trying to predict poverty outputs, we kind of do, a standard technique. It's called cross-validation, where we basically split the data into, say, 10 different folds, and then we'll train on 9 of those folds and then test on the 1 remaining fold. And then we'll do that for all 10 folds. And then we'll average the results across those folds.
Okay, thank you. The next question with a hand raised is from Steve Brody. Steve Brody. Steve?
Hi, thanks. I think it was the slide where you were showing the neural network that took the data in of the images and then generated a feature list which was used for predictive purposes. So yeah, so the CNN generates these features that are then used to predict poverty, correct?
Yeah.
Is the output of the CNN those feature points or feature data items, is that data that's generated available at all to the public so that they can use those outputs for possibly other algorithms?
Yeah, so we're actually kind of working on making that available right now. And I guess maybe that would be good feedback if people would be interested in using that. The reason we haven't made it available yet is because it's kind of to do with the source of imagery that we used. Originally, we were using imagery that we got from the Google Static Maps API. So there's kind of some uncertainty about whether or not we're able to distribute products derived from their imagery. So we're kind of working through that right now and looking into using imagery that's like completely in the public domain, for example, Landsat, and then we definitely would be able to distribute like these feature vectors that are feature maps that are derived from the imagery.
All right, thanks very much.
Yeah, is that something that people would be interested in using, or that would
Well,
be helpful for us?
I can only speak for myself and my activities. I don't know generally if it's interesting to others, but it's interesting to me.
Okay, cool.
Thank you, Steve. We have a question from Jerome. You should see the question, Neil, but I'll read it for everyone else. His question is, what other processes do you think about to improve evaluation of generalization in countries where there are currently no reference data available?
Right, so in countries where there's no data, we can't really evaluate our predictions. So we can make predictions anywhere where we have imagery, but we can't validate like the accuracy of those predictions unless we have some ground truth data. So I guess what we're thinking about is we've been talking to kind of various organizations who actually have the capacity to maybe do some of this like on the ground validation. So I guess that's the direction that we would kind of take it in. One other thing that we could do is try to predict different types of outputs, and then we might be able to kind of use the proxy, use accuracy on that output as a proxy for accuracy on these outputs that we care about. So this is in the case where maybe some type of ground truth data is available, but the ones that we're currently predicting are not.
Great. Jerome, my apologies, I should have unmuted you. I'm unmuting you now. I wonder if that answered the question, or if you have any follow-up you'd want to ask by microphone.
No, that's great, thanks. Yeah, I was wondering whether the strategy would be to ask to get some data in places where there is no current data and select those places with respect to the algorithm outputs. But that's it. Thank you very much.
Good. Thank you, Jerome. We have a group from Columbia University. So the question is, Neal, have you been able to compare poverty estimates over time for any countries for which there is daytime imagery, lights, and poverty data at 2 time points?
Yeah, that's a really good question. We have not done that yet. So the original image source that we were using, the Google Static Maps API, only provides imagery for one snapshot in time. But these new sources that we're looking at, like Landsat, obviously go back in time. So we would start to be able to make these kind of historical predictions. And that's something that we're kind of currently working on. There's definitely a lot of issues there. For example, most of these surveys that we're looking at are kind of cross-sectional. So they don't really track the same population over time often, and so it's just kind of hard to figure out how to aggregate up survey responses so that they're kind of comparable over time if we want to make these time series predictions.
Good. Thank you. Thank you. The next question is from Africa Flores.
Thank you. Can you hear me?
Mm-hmm.
Yes, we hear you.
Yeah, my question is about validation. There was a previous question too, but it's more about the results. Have you done any validation of the poverty results that you have?
Yeah, so I guess kind of like I was saying earlier, so for example, if we're trying to predict poverty in, say, Uganda, we're doing this at the cluster level in these surveys. So if there's like, say there's 400 clusters, we'll divide that into kind of 10 sets of 40, and then we'll use 9 of those sets to train our model, and then we'll evaluate on the other 40 points that the model hasn't seen. So by doing this kind of cross-validation process, it gives us an estimate of the accuracy of our predictions that we would be able to make on places that don't actually have ground truth data.
Yeah. Thank you.
Does that make sense?
Yeah, thanks.
Okay, great.
Thank you, Africa. Thank you, Neal. We have a question now from Bruce McCormack.
Hi, Neal. The question is, if you're getting R squared of, say, 0.42 or one of those numbers, my understanding is that 60-odd% of the variance is unexplained, and therefore is 40% odd of the explained variance. Is that good enough in real practical terms?
Right. So as a grad student, I'm probably not the person who can really answer that question. And I would imagine that it definitely depends on kind of the application that you care about, whether or not that's good enough. So I think for some applications, it's definitely better than nothing. For example, if you want to kind of narrow down the number of locations that you want to focus on to send people out and actually visit, and then like it can kind of maybe help you more efficiently make decisions if those are the kinds of decisions that you're making. And I know some of these R squareds, they seem pretty low, and that was kind of our initial impression too, especially mine because I'm not really familiar with kind of previous work in these areas. But we do compare against other methods of making these types of predictions. For example, in I think January this year, there was another paper in Science where they used call detail records, so cell phone data in Rwanda to make predictions on asset-based wealth, also at the cluster level. And we were able to kind of beat the R squared of those predictions using the satellite imagery. And kind of, it's kind of interesting that you're able to do that because cell phone records are obviously kind of individualized and you can localize these things very well. Whereas for the satellite imagery, there's actually a lot of sources of noise. For example, something I didn't mention earlier was that in these surveys, the cluster locations that are reported with some location jitter, so up to 2 kilometers in urban areas and up to 5 kilometers in rural areas. And they add this jitter to kind of protect the privacy of survey respondents. But this jitter actually just adds noise to our approach because when we're sampling these satellite images, we don't even know for sure that they're from the location where the actual cluster is that we're getting the ground truth data from. So it's kind of maybe surprising in some ways that this method does as well as it does. And if you could actually get the raw data, like the true locations, then you might actually be able to improve performance even more.
Okay. Just another supplementary question. Are you aware or do you think that there's any other machine learning tools which could maybe push the R squared up to, say, 0.7 or something like that? Is there anything out there which could maybe raise the R squared?
Yeah, so there's definitely a ton of things that you could do to try to bump up R squared. So I guess this project was more of just like a proof of concept, and there are a lot of aspects that we didn't really have time to, a lot of design choices that we didn't have time to fully like optimize over. For example, the neural network, the CNN that we used, was a model that was used in the ImageNet competition from 2013. So since then, there's been a lot of progress in computer vision. So if you just swapped out a more powerful neural network architecture for what we were using, you might be able to see immediate improvements from doing that. There's also other sources of passively collected data that you could incorporate into these predictions. For example, you could have the neural network extract these image features and then concatenate that with other features that you get, for example, like weather data, or you could use multispectral inputs, or you could combine this with the cell phone records that I was talking about, and just train a neural network on top of all these inputs together, and you could probably get some boost in performance that way too.
Okay, thanks a lot. Okay.
Thank you for the question. We have a question now from Suraya Prakash, but they've asked me to read the question. I think there's a mic problem. The question is, what resolution of images are used, and what are the grid stroke pixel sizes used for evaluation?
Right, so for the nighttime lights images, each pixel there represents 1 square kilometer. So the nighttime lights data set that we use is the DMSP. And for the daytime satellite images that we used, the pixel resolution there is 1 pixel corresponds to 2.4 meters on the ground. And each image that we used was 400 pixels by 400 pixels, so it also covered approximately 1 square kilometer.
Okay, thank you. Pawan Gupta has 2 questions.
Hi, this is Pawan. So my first question is, I think coming back to the learning pattern, are these machine learning is based on the shapes, textures from the imagery, or are they based on the intensity or some other quantitative parameter?
Right, so when we're training the neural network, we're not telling it what kinds of things to look for. For example, like we're not telling it to look for roads or to look for buildings. We're just supervising the training process by giving it the corresponding nighttime lights value for that daytime satellite imagery. So by looking at lots of these images, it learns, for example, that when it sees a very high density of buildings, that corresponds to a higher nighttime lights value. So by seeing lots and lots of these images, it learns automatically to identify features in the daytime satellite imagery that are useful for predicting nighttime lights. And then we use those features to predict poverty because we think that some of those same features are going to be meaningful for poverty, just as they were for nighttime lights. Did that answer your question?
Yeah, that's fine. And then the follow-up question is basically, are you using any specific machine learning package, or you're developing your own codes?
Oh, yeah. So actually, for this project, we had so in terms of like programming language, we try to do everything in Python.
Okay.
There's a lot of kind of nice machine learning packages that have been written for Python. One that we used to implement the ridge regression was it's called scikit-learn. And for the deep learning part, we had used Caffe, which is kind of it's a framework from Berkeley that's kind of for computer vision applications. But since then, we've switched our whole pipeline over to TensorFlow, which is on Python.
Okay, thank you. I have one quick question if we have time.
Yeah, no problem.
Just going back to the resolution, these, do you think, what kind of the limiting resolution which you can use from satellite imageries to address this kind of applications? Means Landsat is 30 meter, then we have another visual sensor which are kilometers in resolution, or then we have the Googles which are sub-meter or those kinds. So do you have any idea on what's optimal resolution?
Right. So we've looked at we've done a little bit of work on this, looking at different resolutions, and we kind of noticed that at kind of as you would expect at different resolutions, the model learns to pick up different types of features. So at lower resolutions, it kind of picks up on more infrastructure type features, and at higher resolutions, it kind of learns these more detailed features. For example, at I think zoom level 19 or 18, I think, which corresponds to roughly like around 0.8 meters per pixel. One of the features that we learned was a filter that looks for swimming pools, which I guess are a pretty good indicator of non-poverty. So at different resolutions, you kind of learn to find different things. And if you're trying to predict poverty with those features, I think the higher resolution imagery generally does a little bit better.
Okay, thank you.
Yeah.
Fantastic bunch of questions. Thank you, everyone. The next question is from Africa Flores, again, a follow-up, but I think it's probably been answered in the last response. The question is, do you think there is any potential in the use of medium resolution data for this type of analysis? I think you've answered that question, yeah.
Yeah, so I do think there's potential, and that's kind of where we're looking at going. So there's also one other thing we had looked at was kind of building a multi-resolution model where we would kind of extract features at all of these length scales and then kind of use all of them to together to predict the things that we care about.
Great, thank you. And then the last question in the queue here is from Sandra Blevins.
Oh, hey, great talk. Thanks so much. It was really interesting. I was just curious of the end users that you guys are targeting. I know you mentioned a couple of NGOs at the beginning of your talk, but I just wondered if this work has been put into action yet, and is it impacting any communities that are, poverty stricken, or what sort of populations do you see this work helping and improving the lives of?
So as far as I know, no one's actually using it yet. I think part of that is because we haven't really been able to kind of freely distribute like the outputs that we've produced. And yeah, so our original motivation for doing this project was that we hoped that it would be something that people would actually be able to use. We didn't want to do it just, to kind of publish it academically and have it sit in the corner. So, for example, we've been talking to people at the World Bank, and they're kind of building on this and maybe developing some of these similar techniques in-house. So if people end up using, I think people might end up using this technique more than they end up using directly the outputs that we've produced. Mm-hmm. So I guess I'm maybe not in the best position to predict how people are actually going to use it because, I do computer science research. I don't actually work on these problems. So you guys might actually have a better idea of how people might use these kinds of things than I do.
Yeah, that's great. I was just curious if you knew of anybody currently using it, but no, that's wonderful. It's great work. And I just have one last question. I kind of lost my connection, so you may have already talked about this. But can this sort of work be scaled down to like inner city levels, like on a statewide sort of city? And it'd be difficult with all the different features that you input to your models. But what can you say anything about that? That'd be really interesting to look at.
Yeah, so I think it
for
can
example, or like Washington D.C., or spanning out to yeah. Go ahead.
Yeah. So we thought about that a little bit. I think definitely the general idea of using satellite imagery to make predictions on these outputs that we care about, that is definitely something that can be transferred to these urban settings. The way that we actually go about doing that would definitely have to change. For example, right now we kind of train on a coarser level. So in urban areas, you can have very poor areas right next to very rich areas. And our current model would not be able to tell those apart, I don't think. But if you have higher resolution imagery and you have kind of finer grained training data, then you can definitely, so kind of one rough metric that we use when we're talking about these types of computer vision problems is we start by asking ourselves, is this something a human can do? So you can imagine that if you went on Google Maps, the satellite view, and you looked at very high resolution imagery of an urban area, you could, with some confidence, not full confidence, but some confidence, start to make some statements about whether you think an area in a city is rich or poor, just from that satellite imagery. So if a human is able to do that with the right types of training data, you should be able to train a computer to do that. And actually, if I can go back to your previous question, I just thought of, there is a group that's already kind of using the output that we produced. And what they're doing is they basically took one of these maps of poverty that we've provided, like for this one of Uganda, for example, and they kind of overlaid on this predicted poverty map a map of their own organization's operations, and that kind of gave them a rough idea of whether or not they were working in the right places. So that would be one application where you could start to use these predictions right away without being too worried about, oh, like what is the R squared? Yeah.
Thank you. There's one last question, I think, from Steve Browdy.
Okay, thanks. Yeah, I wanted to go back to the R squared discussion. Unless I've missed something, I think one of the slides you showed, the R squared is being generated based on a linear regression, correct?
Mm-hmm. Yeah.
Yeah. Is the linear nature of your regression technique is that your assumed default regression, or have you looked into other functional regressions techniques, like, for instance, generic polynomial regressions or splines and things like that that might fit the data better, or is it always the case that you're using linear?
Right. So that's kind of one of the things that we haven't really optimized over, and kind of the reason we decided to go with just something simple like linear regression is that we felt like it made the model a little bit more interpretable. There's already enough that's hard to interpret coming from the neural network, so at least with a linear regression you can kind of say, okay, if we change this feature, then like what's going to happen to our prediction. Yeah, but no, we didn't really like kind of search over the space of all models here.
Okay, so that would be, in your opinion, I guess I'm asking, would that be an area for open research then with this study?
Yeah, that could be.
Okay, all right, thank you.
Yeah, no problem.
Really would like to thank Neal for giving us his time. It was an excellent presentation. As I said, we broke all records in terms of the number of registrants. You bear in mind that only a fraction of the people who will see this video are actually here live because of the diversity of time zones people are in. I think the questions we've had were excellent. I thank everyone for doing that. I think, Neal, it was probably a good practice for your PhD defense, I would imagine. It's very thorough grilling from the people here. So thank you once again. To tell you about the two upcoming webinars that we have in our series. There are several more where we're finalizing dates and times with the speakers, but the next two that are confirmed, the next one is by Alessandro Gali and Elena Gnezevec, and they are going to be talking on the development of a national strategy for sustainable development for the country of Montenegro. That should be fairly interesting. And that is on December the 1st at 1 p.m. Greenwich Mean Time UTC. I will be sending out a proper invitation as we did with Neal shortly, so watch your mailboxes for that, please. And on the 15th of December, we have Ed Parsons, who many of you will know, people who attended the Iron Earth Summit 12 months ago. He is the geospatial technologist at Google, and he's going to provide us a briefing and update on the OGC W3C spatial data on the web working group. So that should be interesting. That's on the 15th of December at 1:30 GMT. And again, I was sending out formal invitations. There are, as I said, a number of other, at least 3 more in discussion for in the new year. So our discussion to an end. So if there are any questions, my email address is there. If there are any questions for Neal, then either contact him directly, or I'm happy to route them to him. Again, you know, I can't thank everyone enough. This is a knowledge sharing community. It's what we make it, and when we have great speakers and great professionals, practitioners from the field coming together like this, I think it's a great use of everyone's time. So with that, I will bring the webinar to an end. Just to give a final word of thanks to all the participants and attendees for not only for attending, but many of you have shared the invitation with your professional network, and consequently we see a number of new names here, and I thank you for doing that.